Okay. So, in the last class we we talked about the TPC, TPI, that is the tons per centimeter immersion and tons per inch immersion, the amount of weight that needs to be put to produce a centimeter of submersion of any body. So, after this we will now take a look at some of the some other phenomenon that goes along with this. This is known as the trimming. So, trim is a phenomenon that is associated with a longitudinal submersion. That is, if you have a ship like this and if the ship goes in any of these direction, if it oscillates about this degree of freedom, then it is known as trimming. Okay. So, trimming, the other one which we dealt about till now was about the ship. In if this is the longitudinal direction, if a ship is able, if ship is made to oscillate in this fashion, it is known as heeling. So, heeling, we are now going into trimming. The same way as you see heeling, that is, we have the kg, kb, then LCB, kg, kb, etc., and the meta center, the new position B phi, the meta center, we discussed all that, and that is all seen through a transverse direction. That is, the view is from the transverse direction, that is, if the ship is like this, we are seeing it from here. So, it is a transverse view. Now, suppose we see the same thing in a longitudinal direction, means like this. This we usually call it as a profile. So, we are seeing a ship like this. Okay. So, this kind of profile will, this is another phenomenon that will occur in the ships. Now, we, instead of seeing these meta center, the center of buoyancy, etc., in a vertical direction, in a transverse direction, we can also see the same thing in the longitudinal direction. That is, if you see the same, we are going to follow the same principles between the transverse direction. The only thing is the difference between the transverse direction and the longitudinal direction. Other than that, all the principles remain the same. There is a meta center M, there is a center of buoyancy B 0. It is because of the trimming, instead of heeling. Remember that we were talking about heeling in the previous section. So, instead of that, if the body starts trimming, because of that trimming, there is a shift in the center of buoyancy like this. For example, I will draw this figure. So, this is the initial, let me draw it better. So, this is the ship, and this is its water line. This is its water line, initial water line, and because of its movement, it causes it to trim like this. Okay. So, the ship is now trimmed through an angle theta. I would like to mention that usually heeling is denoted, heeling angle is denoted by phi, and the trimming angle which I have drawn there, this is known as the trimming angle. The trimming angle is usually denoted by theta. So, you have theta, the trimming of the ship, and this is the, let us assume this is the forward side of the ship and this is the aft side of the ship. So, we define it like this. This distance is known as trim by head, and this distance is known as trim by stern. So, the front part, the amount by which the front part trims from the mean water line. So, there was an original mean water line, the distance from which it trims, that distance is known as the trimming by head, and the aft side of the ship, the distance through which it trims is known as the aft, that is known as the trimming by stern. So, we have this trimming, and there is a slight ambiguity or vagueness about what you really call as the trim. For example, trim can be this in this figure. This trimming by head can be called as a trim, trimming by stern can be called as a trim, or the whole distance between the forward and aftward trim can be called as the trim itself. So, the distance between this distance, between this and this, between this and these two, this distance can also be called as the trim. In to prevent ambiguity in our course, we will define the total distance between the forward topmost part and the aft bottommost part. The distance between those two we will call it as the trim. This is the distance through which the ship has totally tilted. Okay. So, we now have a ship like this. So, as you can see, we always assume that the it is not really an assumption, it is always true that the amount of ship that has gone down, that is submerged part of the ship, is equal to the emerged part of the ship. It is valid to some extent, and that principle we are assuming here. So, trimming by stern is most likely equal to the trimming by head. So, the trim by stern and trim by head are both almost equal in magnitude, and therefore, the total trim is twice this value, twice the trim by head or twice the trim by stern. So, it is twice this. So, that is what we will assume in our study in our lectures. Okay. So, this figure I will keep here. Okay. Then this distance, now for our purposes, let us do one thing. Let us consider a rectangular barge, that is a barge that is with a rectangular shape. This is the rectangular barge. So, this is the water line W L. So, this is the rectangular barge has trimmed through an angle theta. So, initially let us assume this to be its center of gravity. G is its center. Let us assume it a little below. Let G be the center of gravity, G 0, and B is even below this, B 0 is the center of buoyancy. So, as you can see here, we are seeing things from a longitudinal perspective or from a profile perspective. It is no longer from the transverse direction as before, and we are not dealing with heel here, we are dealing with trim here. Trimming is dealt with in the same manner as you deal with the healing, and therefore, you have the position of G 0, B 0, and because of this trimming, the B 0 shifts to B 1, and if you put a vertical from B 1, it will hit the vertical from initial vertical from G 0 at the meta center. This is the meta center that we are seeing from a longitudinal perspective, that is, we are seeing the profile of it. This meta center, which we are seeing as a profile, is the meta center due to trimming or the shift in the, here the shift in the center of buoyancy is in the longitudinal direction. So, as you know, this shift in the center of buoyancy is known as LCB. This center of buoyancy, here we are dealing with the longitudinal center of buoyancy, that is what I mean. So, that is the initial position and the final position of the longitudinal center of buoyancy. The previous healing dealt with the transverse center of buoyancy, which is in short called the center of buoyancy, B 0. this is B0 in the longitudinal direction. So, okay, and similarly this M that we see here is no longer designated as M, it is called as ML. So, B0 ML is the longitudinal metacentric radius, and G0 ML is the longitudinal metacentric height. Okay, so it shifts like this. Then we can draw a perpendicular from G0 to this line. This is a perpendicular, we will call that ZL. As you remember before, we called GZ to be the writing arm. This is the restoring arm, or or this is the arm which causes the ship to come back to its original position. In the same way, when the ship trims, still a restoring arm is produced again, a longitudinal restoring arm, that is GZL. So, GZL will represent the longitudinal writing arm, it is known as the longitudinal writing arm. And therefore, here at B0, through this initial vertical there is a horizontal line delta, and through this there is another force delta acting. So, here you have the weight delta, and here you have the, in the final state, that is when the ship is trimmed, you have the center of buoyancy here, and through that center of buoyancy acts a force delta, that is the weight of the ship that is equal to the weight of the ship, because the ship is floating. So, delta, the weight of the ship, acts upwards acts as the buoyancy force, it is called. The buoyancy force acts upwards along B1 in the vertical direction, and between this and this, the vertical distance GZL produces a writing arm, when because of this force and this writing arm, it produces what is called as a writing moment. So, in this case we get a writing moment which is given by GZL into delta, it is equal to delta into GM sin theta. Now, GML sin theta, ML sin theta, this is the same formula that you remember for healing. We discussed about the restoring arm and GZ, and we talked about the restoring moment delta into GZ. This, and we have said that GZ is equal to GM sin phi for healing. Same principle is holding here. Delta GZL is the longitudinal writing arm. So, delta GZL is equal to delta GML sin theta. Okay. Then let us look at this figure again. Let me draw a horizontal here. As this is the first station, this is the last station, the distance between these two is known as LPP, distance between that is known as LPP. So, tan theta here, so it is clear. So, tan theta is equal to this distance divided by LPP, which is, now let us assume that the ship has trimmed by by 1 meter. So, we are going to assume that the ship has now heeled by 1 meter. Therefore, what is tan theta? Tan theta is equal to that 1 meter divided by LPP, as you can see from the figure. 1 meter, this distance, this distance is the trim, and we are now going to assume that this trim is 1 meter. So, 1 divided by this distance LPP, this distance will give you the 1 by LPP will give you the the tan theta. So, tan theta is equal to 1 by LPP, and same principle holds good for GML, that is equal to KB plus BML plus minus kg. Okay. So, this formula holds good even for the longitudinal metacentric and longitudinal metacentric radius and height, and this is the expression for GML here. Now, the usually you see that the heeling, we have seen that heeling goes for the heeling of a ship goes between an angle of about 3 degrees to about, it can go up to 30 degrees, 40 degrees heeling. Now, for a trimming, we do not talk about, we do not encounter such large angles, because mainly in the other case we were looking at the breadth of the ship as the denominator of phi of tan theta, whereas in this case we are looking at the length of the ship as the denominator, which is very large, as a result of which the length is very large. So, as a result of which the tan theta is very small. So, we can assume that the writing moment is equal to delta GZL equals delta GML sin theta, and delta GML sin theta is approximately equal to delta GML tan theta, and we have seen here tan theta is equal to 1 by LPP, that is equal to delta GML by LPP, and this expression gives you the restoring moment to change the trim by 1 meter, and this is known as MCT. This is a very important term. It is used in many places. You will find its application coming up. This is known as MCT, the moment to change the trim by 1 meter. The moment to change the trim by 1 meter. So, this is some definition about trim. We will have to do more about trim and the longitudinal metacentric height and all that in a later lecture. We will be doing about it. So, right now this is okay. Then let us talk about a couple of important parameters that we have discussed so far. The first of which is the trim by head. This is the first important thing that we learned in the previous few lectures, trim by head. Then we have trim by stern, trim by head and trim by stern. Then volume of displacement, this we know what it is, we have described it many times. Then LCB, so LCB is the longitudinal center of buoyancy. So, this is another parameter that we discussed about. Then LCF we talked about, this is known as the longitudinal center of flotation. Longitudinal center of flotation is the centroid of the water plane area, we have discussed it. So, this is known as the LCF. Then we talked about moment to change the trim, MCT, moment to change the trim by 1 meter. This is another important phenomenon, another important term. Then we have Km, which is the you know what is Km, it is the distance between the keel and metacenter. So, Km. Then CB, this is the block coefficient. then a couple of other coefficients like Cm, C, W, etc., the water plane area coefficient, the midship section area coefficient, and so on. So, these are some of the important terms that we have discussed so far, and Kb, another one, it is the Kb is the vertical center of, it is the vertical center of buoyancy. Okay. So, these things are known as hydrostatic particulars, or it is known as hydrostatic data. Note that all the terms do not come under all the details of the ship do not come under the category of hydrostatic data. Only these things, only these terms will come under the category of hydrostatic data. These are some of these hydrostatic data, as I said, are some of the particulars of the ship itself. It is not got anything to do with the loading, the transfer of loading, and even though some transfer in loading can produce some changes in this, the G factor, the Kg or Kg or Gm do not come under the category of hydrostatic data. We do not call them by that name. Okay. So, next is something known as the there is another term which we use commonly. This is known as the wetted surface area. Known as a wetted surface area. Wetted surface area means the total area of the ship that is subjected to the water. So, total part of the ship that is wet is known as a wetted surface area. So, if you have the ship like this, the whole region that is wetted is known as a wetted surface area. Then we come to wetted surface area. Why is the wetted surface area important? There are a couple of parameters that depend upon the wetted surface area. They are mainly the resistance of the ship. That is, just to give a quick review of resistance, this is another course, resistance and propulsion, in which you will be doing things in greater detail, but here I will just mention some of the details of resistance. So, the resistance of the ship is really divided into two types of resistances. One is known as the wave resistance, and the other is known as the viscous resistance. So, these are two types of resistances. One is the wave resistance, and this is due to the pressure on the hull. So, the wave resistance is due to the pressure on the hull. This and viscous resistance is due to the friction or viscosity. So, this are two types of resistances you encounter in ships. The wave resistance depends upon the form of the ship, that is the form of the ship. It defines the pressure distribution along the hull of the ship, and the pressure distribution, for example, a pressure difference can produce a force. So, there will be a high pressure on the forward part of the ship, and there will be a low pressure on the aft part of the ship, and therefore, there will be a force acting from the forward to the backward side, which is the resistance that the ship encounters while it moves forward. This is known as the wave resistance. This generates two waves in a particular form in the back of the ship. They are known as Kelvin waves, Kelvin wave form, and the other resistance is the viscous resistance, which is the frictional resistance. The frictional resistance is also important, and depending upon the type of ship that you have, the one resistance or the other resistance will predominate. Very large ships like container ships and oil tankers usually have a very high viscous resistance. Okay. So, that is about the wetted surface area of the ship, that is the amount of ship that is subjected to the wetting. Then in this we come to what is known as the hydrostatic curves. So, the hydrostatic curves are curves that are drawn in this format. Remember, we put a lot of parameters here, and I told you that these parameters are known as hydrostatic particulars, starting from Kb, Cb, Km, Mct, etc. All these are hydrostatic particulars. If I do a graph of draft versus any of these parameters, if I drew a graph between the draft and any of these parameters, curves that look like this, different things, it could be Cb, it could be the MCT, it could be the LCB, LCF, etc. all these things as a function of draft, this is known as a hydrostatic curve. So, these things are hydrostatic curves, and as you can imagine, okay, and another important hydrostatic curve is the one related to sectional area. I have already explained to you what is known as the sectional area. If you have a ship like this, and if you have a slice, if you slice the ship like this, these areas are known as the sectional areas. This area, that is the part of the area that is under the water and through which you have produced the slice. So, this is known as the sectional area. So, you can draw the sectional area at various drafts, that is also a hydrostatic curve. So, sectional area you will have like this. These sectional areas with draft, each of them, as you can imagine, the sectional area will depend upon the station at which you are studying. So, this station, this could be station 5, this could be station 4, and this could be station 3. So, these stations are so you have a slice through a particular station, and you will, the area under the curve is known as the hydrostatic curve. So, this sectional area curve, such curves dealing with the sectional area are known as Bongian curves. The word used is Bongian curves. Then and sometimes usually you draw different curves with you draw different of these curves, that is at different stations, starting from one station 0, for an instance, the aft station 0, 1, 2, 3, 4, 5, like that. We draw the we can draw the Bongian curves for different stations, and this will produce another sectional another kind of another curve. The whole curve is known as a Bongian set. So, this Bongian set will give you the Bongian curves at different points, different stations. Then we have the definition for sectional area. The sectional area is defined as A is equal to actually there is not even much of a need to explain this. This is the sectional area. Sectional area is the region under the water line. It is the region under the water line of one particular station. So, here you are summing up the area from the bottom, the baseline, to the water line. So, like this. So, if you have a ship like this, water line like this, this is a particular station, and you are summing up the area for this particular station. So, this is not, this is y dz integral from keel to the particular draft. So, this is the draft T, this is the keel to the particular draft is known as y dz. This is known as the sectional area, is the how the defined. Now, we can also have another thing which is the moment from baseline. This represents the moment that you take about the baseline for each of these. So, what have we done? We have divided this into different delta t's, that is what this dz stands for. Dz is different delta t's. If I had to write this, it will become sigma n equals 1 to some capital N of y I delta t, where delta t is the into alpha, where you have the Simpson's multiplier. So, alpha I into delta t, where delta t is the distance between the different water lines. So, the moment from the baseline is known as m equals from keel to t z into y dz, z into y dz. This is known as the sectional area as a function of draft. So, this is known as the moment from the baseline. So, moment from the baseline is z y dz. For instance, let us look at one problem. We make what is known as a Buoyancy sheet. This is how it looks like, Buoyancy sheet. Now, we can also, before we do this, we can see that there is another parameter that we can derive from this. This is the moment from the baseline, and this is the sectional area. And if I found out the moment from the baseline divided by the sectional area curve and summed it up for the entire stations. So, what I am saying is that this area into for the entire station will give you the total volume under that. This gives you the total volume, and this gives you the total moment. And if I divide the total moment with the total volume, what will I get? So, the total moment divided by the total volume will give me the Kb. Okay. Kb is the is the vertical center of the position, vertical position of the center of buoyancy. Kb is the total moment by total volume. So, similarly, you will have you can make the Buoyancy sheet like this. So, you have the station number, then trapezoidal multiplier, lever arm, sectional area, AI, lever arm Ji, trapezoidal multiplier alpha I, then functions of area, alpha I AI, then moment above baseline, that is Mi, then functions of moment about the baseline alpha I Mi. Then you can also have one more, you can have the moment from midship, alpha I Ji AI. So, the moment from midship, so this is 1, this is 2, 3, 4, what is 5? 5 is equal to 2 into 4, 6 equals 3 into 5, 7, 8 equals 2 into 7. So, 0, half. This is how they have made the stations. This has nothing to do with the problem as such. I mean, the way in which the problem is solved, it is just the way in which they have solved it. Means they have a station at 0, they have a station at half. You know what are these half ordinates? So, you have a station at half, then you have the next station at 1, 1 and a half, 2, like that, like this. So, 1 half, 1, and the corresponding trapezoidal multiplier which we have done will come later as 1 by 4, 1 by 2, 3 by 4, like that. Lever arm, as you see, this is the lever arm from the station, from the initial station. So, you can do it two ways. The lever arm can be taken in two ways. One is you can always take the lever arm from the station 0. So, you put the station 0 as 0, then 1, 2, 3, 4, 5, like that, and or you can have the midship as station midship as lever 0, and one side to the forward as positive and one side to the aft as negative. So, that is another possibility. So, you have like this, and area equals, when you do this, sigma function of area, this is sigma moment, and this is sigma moment again. No, not this one. So, this one. Sorry, this is sigma moment 1, and this is another sigma moment. These are two moments. One is a moment taken from the baseline, moments of each of the areas above the baseline, and the other one is the moment from the different stations, moment of the different stations. So, using this sheet, we can calculate the this is known as a Buoyancy sheet, and using such sheets you can calculate the that you can always calculate the total volume under the from this with multiplying it by h by 2 into sigma function of area. You will get the total volume of the underwater portion, or volume submerged. You will get the volume submerged. And what is the use of the moment? What is the use of the sigma moment from the baseline? The sigma moment from the baseline divided by sigma function of area will give you the sigma moment from baseline divided by sigma function of area will give you the Kb. Okay. So, this gives you the Kb, and similarly the sigma moment from station 0, divided by sigma function of area will give you the LCB, the longitudinal center of buoyancy. So, this holds good, and so in this way you can calculate the LCB and the Kb for such ships. You can find the volume, you can find the LCB, you can find the Kb. All of that is possible from a Buoyancy sheet. So, you can see the importance of Buoyancy sheet. So, most of you who will go into the naval architecture career in shipyards or consultancy companies, they will be doing a lot of these Buoyancy sheet work. You will have to definitely calculate the volume under the submerged, that is known as that is a volume submerged, and the LCB, Kb, etc. you will have to find out. Okay. Now, that is one thing. Then let us suppose we have a body okay, and let us suppose it has an initial water line WL and it has a final water line W1 L1 and it has dipped through an angle delta t. So, the body initially at WL has gone up to W1 L1 because it has dipped or submerged by an additional amount of delta t. Now, we can see the problem that we are going to define in two different ways. The first one is the change in moment the first one is that the change in moment of volume, change in the moment of additional volume is equal to the moment of additional volume. Change in moment is equal to the moment of additional volume. So, the change in moment, okay, let us take the initial volume, and the change in the moment is given by delta of x b, where x b is the center of buoyancy, into del. This represents the change in the moment of the additional volume. So, the change in the moment of volume, this delta represents the change in the moment of volume is equal to the moment of the additional volume. What is the additional volume? Additional volume is A w into delta t. So, the additional moment is A w into delta t. A w is this. Now, remember this delta t is very small, therefore, A w does not change as we go in this dipping. This submerging, because of this submerging, the A w does not change. This is because of the assumption that the delta t is very small. Therefore, A w into delta t is the additional volume, and where does this additional volume act? The additional volume always acts at the centroid of the additional area, centroid of this water line. So, the centroid of the water line of the centroid of the water plane area, or the centroid of the that water line area is known as the center of flotation, x f, the center of flotation. So, x f into A w delta t will give you the moment due to the additional volume. So, there is a slight difference between this and this. The difference is that this is the additional volume into where it is acting, x f is the moment due to that additional volume. This is the change in the moment itself, it is the change in the moment of the volume. So, change that moment of volume is what? Volume is the moment the volume itself acts, we can assume that the volume itself, total volume of the underneath acts at x b. X b is this longitudinal center of buoyancy. So, at x b the volume acts, the total volume of the ship acts at x b, and therefore, x b into del gives you the moment of the ship. Now, the change in moment will be delta of that. So, the change in the moment of the volume, let me remove this, it is confusing. So, if I write it like this, it is better. Change in the moment of volume is equal to moment of additional volume. So, you get this concept. Similarly, you will have delta of y b into del equals y f A w delta t, delta of z b into del equals z f into A w into delta t. So, you have three formulas here. Now, we can expand this. This is a product of two terms. So, you know that you can expand a derivative of the product of two terms. So, that will give you delta into delta x b plus x b into delta of del is equal to x f into AW into delta T and del of delta YB plus YB into delta del equals YF into AW into delta T del of delta ZB plus ZB into delta of del equals ZF into AW into delta T. Okay. So, this gives you the some terms. Then now dividing by delta del equals AW delta T, this reduces to, if you do some manipulations, this reduces to XB minus XF minus XB is equal to d of XB by dt del by AW and YF minus YB equals d of YB by dt into del by AW. Now, what does this mean? In a case when XF is equal to XB, so which is like saying that where the curve of the longitudinal center of flotation meets the center meets the curve of center of meets the curve of the longitudinal center of buoyancy, the dy by dt is equal to 0, like this. So, if XF equal to XB, then XF minus XB is equal to 0 is equal to dXB by dt. So, this implies that the where the curve of this is a very important thing. So, what that implies is that if the curve of the center of flotation intersects the curve of the center of buoyancy, then XF is equal to XB at that point. So, XF minus XB is equal to 0 is equal to dXB by dt. So, what does it mean when dXB by dt is 0? That means that this curve of XB versus draft will be vertical. The tangent at that point, the tangent will to the latter curve, means the tangent to the center of buoyancy curve will be vertical. So, this is an interesting and useful useful derivation which you will be using in some places. So, where the center of flotation intersects the center of buoyancy. So, where the center of flotation intersects the center of buoyancy, the tangent to the latter curve, that is the center of buoyancy curve, will be vertical. Okay. Then if we do a little more mathematics, XF minus XB divided by ZF minus ZB is equal to dXB by dZB. That is just I just divided the two together from one from the I just divided one from the other. Therefore, similarly, so this is just used like that in some places. XF minus XB divided by ZF minus ZB is equal to dXB by dZB is another formula that is used in some places. So, there is an LCB curve and there is an LCF curve. So, you can have an LCB curve and an LCF curve, and when you draw them together in the draft, so it will be like this. No, draft will be here. So, you have the draft and here you have the LCB curve and LCF curve. So, one curve is like this, one curve is like this. So, at that point, if this is the LCB curve, the tangent to the curve will be vertical. So, this interesting derivation you should take home today. So, with that I will stop today's class. I will stop today's lecture. Thank you.